In this lecture, we're going to take a look at the mechanism of how light is focused. And when we think about the focusing components, all of the items that or all of the anatomical features that were addressed on the previous videos are involved in focusing, but the major focusing component of light is the lens, and that's highlighted here on the upper left-hand part of the slide here in our diagram of the eye, this blue portion being the lens. And the ability of the lens to focus is referred to as accommodation. And accommodation is a short-term change in the structure or characteristics of some anatomical feature here. And with respect to the lens can undergo a very short-term change in shape, and in doing so, can change the focus. In other words, it can change the image in terms of the distance to the object. And the way this is carried out is through the ciliary muscle. So the ciliary muscle has the ability to contract, and that's what's pictured here on the bottom part of the slide here. The ciliary muscle will contract, and in doing so, it will relax the zonule fibers. So these are the zonules of Zinn that will form a link between the ciliary muscle and the lens. And these are connective tissue types of tendons, if you will, that will transmit the force produced by the ciliary muscle and the lens. But when the ciliary muscle contracts, it will actually relax the zonule fibers, and that will allow the lens to change shape and focus on near objects. And so what we see here on the left-hand side, here we see the unaccommodated lens and the accommodated lens. Now, the accommodation occurs through a contraction of the ciliary muscle. Uh, Not quite as clear as you can see here on the drawing here. The drawing doesn't make it entirely clear, but you can see a slightly different shape of the ciliary muscle on the right-hand side as you do on the left-hand side, and with shorter fibers. So shorter fibers means the distance between the ciliary muscle and the lens has decreased, making these relatively slack. And because they're not pulling on the lens, that allows the lens to expand, and that will change the refraction of light as it moves through the lens, moving the near objects into a better or a clear focus. Now, when we talk about the focal distance, the lowercase letter F that's italicized is the standard symbol for focal distance. And the ability to recognize near objects is referred to as focal power. And it's simply the inverse of the focal distance, which is 1 divided by the actual distance to the object. That's focal power. And the unit of measure is what's called a diopter. Uppercase D is the symbol. So, in terms of understanding diopters, 15D translates to 1 over 5. This is the focal power, which translates to a distance of 0.067 meters or 6.7 centimeters. And that's the typical distance for reading, near distance reading. And what we see here on the graph is an illustration of presbyopia, myopia. And what this is a condition that occurs naturally, and it's an age-related loss in lens power as a function of age. And so on the graph on the left-hand side along the x-axis, here we see our focal power is highest during the years of adolescence from 10 to 20, but starts to decrease continuously out to the age of 60. And this is a measure of the accommodation ability or focal power diopters, and that decreases as a function of age. What these different symbols are, these are different research studies, landmark studies that have tracked the uh, focal power as a function of age. And as you can see here, although these are different studies, they all found a similar pattern, where the dotted line here reflects a distance of 40 centimeters, which is seen as the breakpoint where the need for accommodating lenses, reading glasses, becomes necessary. In some individuals, the loss is faster than others, requiring earlier intervention with external lenses. And in this picture, we see these pictures here. Here we see not so much the natural consequence of age, but the inherent development of the eyeball in different people. And so different individuals will have different eyeball lengths. Emetropia is a length of the eyeball that has no refractive error. And so what this refers to is that the refraction of light, so light does pass through the cornea, the lens, and through the vitreous humor where it gets uh, uh, where it converges to the posterior part of the eye on the retina. Here, what we see is that the length of the eyeball matches the focusing, the refraction of light to a particular region of the retina. So there's no refractive error. We have it perfectly matched. Myopia is a term that refers to nearsightedness. And if a person is nearsighted, they're able to see closer objects better than distant objects. So they're able to narrow to and focus their vision on items close to their eyes. And that occurs with longer eyeballs. So a person born with a longer eyeball will often need corrective lenses to focus on distant objects. So the longer eyeball is longer than the optimal refraction. The opposite is hyperopia, which is farsightedness, and that's individuals who are able to see farther objects better than nearby objects. So they are able to sight far. And on the left-hand side here, this is an illustration of these three different conditions. Emetropia is the condition where the length of the eyeball matches the perfect convergence of the refracted light rays onto the retina. And the dotted line here, I'm highlighting the dotted line. Let me pull that red line off here a little bit. So the dotted line is an illustration of the eyeball length and where the convergence of light of the refracted light will come to the point of optimal focusing. So with emetropia, the eyeball length matches the optimal refraction. With myopia, we have the eyeball length extends past the optimal point of light refraction, and so that will produce a blurred image for more distant objects. And the opposite of that, hyperopia, here we have an eyeball that is naturally, this is a person is born with this, a naturally shorter eyeball from where the light would refract optimally past the eyeball. So this produces farsightedness, and the person is able to better focus on nearby objects than they are with. They're better able to focus on distant objects than they are nearby objects. And the right-hand side here illustrates the myopic and hyperoptic eyeballs, the longer eyeball, the shorter eyeball, on how corrective lenses and different types of corrective lenses are used to refocus the light so that they will converge to the optimal point at the back of the eyeball or on the retina. So note that the optimal convergence without the corrective lenses are not focused on the retina, but with the corrective lenses will take the naturally longer or the naturally shorter eyeball and uh, make those light refractions uh, to the convergent point on the retina in both situations. So this ends this video on the focusing of light.